Hello, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to talk about 3-2, which is the periodic trends of the IB Chem SL curriculum, and we're going to be looking at these understandings and applications and skills. Let's go ahead and get started. Let's talk about effective nuclear charge. So we know that protons attract electrons. So let's take a look at sodium. All the protons we know are in the nucleus or in the middle of the atom, and they're going to be attracting these electrons. Now, it turns out that the electrons aren't all at the same distance. Then the first energy level is closer than the second energy level and the third energy level. And so what happens is these electrons out here on the third energy level are not as attracted as much as the electrons that are in the first energy level because, one, due to distance, and two, because of shielding, meaning this outermost electron is going to be shielded from the attraction of these protons because of these inner level electrons. So if we look at sodium, it has 11 protons. It's going to be shielded by these 10 other electrons. This outermost electron is going to be shielded by these innermost 10 electrons. And so the effective nuclear charge of sodium, we're going to say, is +1. Now, a couple of terminology that we're going to need to explain some of the following trends are, number one is principal energy level. Those are just those rings or the shells. So here's the first principal energy level, second, third, and fourth. Valence is going to be the outermost principal energy level, or sometimes you say valence electrons, which are the electrons on that outermost level. So valence of 1, valence of 1, valence of 1. Nuclear and effective nuclear charge, we just talked about that, and that has to do with electron shielding, negating some of the effects of on the outermost electron because of electron shielding. And then we should know that electrons repulse each other and protons and electrons attract each other. Let's take a look at atomic radius. Now, if you remember from the previous chapters, it is kind of, not necessarily correct to be drawing atoms with these boundaries like planets. And so the way they actually figure out the size of or the radius of these, they bond two atoms together and then take half of the distance between the nuclei to figure out this distance. And so remember, this line isn't actually a real line because it's supposed to be a probability rather than a distinct line. And so the radius or the size is going to decrease going left to right. The reason this is because we have more protons as we're going from left to right, more and more protons, and as we get more and more protons, they're going to be pulling those electrons closer and closer in because there's more and more nuclear charge, the more attracting those electrons inward. Now going down the table, it's going to increase because remember, every time we go down a level, we gain another one of those rings or another one of those energy levels. This is going to be the 1, 2, 3 rings, 4 rings, 5 rings, 6 rings, and so on and so forth. So it's going to increase going down the table. Ionic radius. What you need to know is that cations are always going to be smaller. That's because they lose electrons. When you lose electrons, the radius is going to get smaller. And anions are going to get bigger. And so when we gain electrons, those radii are going to get bigger. Ionization energy. This is the measure of attraction between the nucleus and the outermost electrons. You can also think of it as the energy needed to remove the outermost electron. So how much energy is it going to take to pluck off the last outermost electron? This is going to increase left to right. That's because if this is the energy to remove electron, and going left to right, we know that there are more protons, there's more charge, there's more attraction, they're being held together there tighter, that's why they're kind of scooting in and radius decreases. And so it's going to take more energy to remove that outermost electron. Now it's going to decrease going down because those electrons are a lot further away from the nucleus and because of shielding. And so it's not going to take a lot of energy to remove that electron that's super, super far away from the nucleus. A couple of exceptions to these trends. Notice that B is to the right of beryllium, so it should be higher, but it's actually lower. That's because you are just starting to fill this p orbital. So the p orbital doesn't have as much energy, right? This is S1, S2, P1. The s orbital is fully filled, but you're just starting to fill the p orbital. So it actually is going to take less energy to knock this guy off than to disrupt this fully filled s orbital. Same thing with nitrogen and oxygen. Here the p orbital is half filled, which is more stable than trying to double up. If you remember Hund's rule, when you get to that fourth electron in the p orbital, you got to double up those bus seats. So that's actually less energy. The electrons don't like to be crammed into that same bus seat. They want to spread out first before they start doubling up. So this is actually less in energy than the nitrogen. Electron affinity. This is the change in energy when an electron is added, but this is only in gases. And so we can see that the more nuclear charge, or the more that they want electrons, the electron affinity is going to be higher. And it's going to be lower over here when the effective nuclear charge is lower. So we can see that it's going to increase going to the right, and it's going to decrease going down. And we can see here the same exceptions that we're seeing before. And again, that's because over here with the s and the p orbital, and over here with Hund's rule and the p orbital. Electronegativity. This is the ability to attract electrons into a covalent bond. So this is how badly pretty much a element wants an electron. Well, notice that fluorine is the most electronegative element in the periodic table. Fluorine really wants those electrons. And so it's going to increase left to right because, again, we have more nuclear charge over here, so we are going to want those electrons more. And it's going to decrease going down because the need to fill those outermost electrons is going to be less because it's at a greater distance and because it's being shielded by those innermost electrons. So here's just a quick graphic that's going to summarize some of the trends that we've been talking about. Some of them we haven't talked about and we're going to be talking about in this second video.